Okay, so today we'll be going through these two questions that was requested by some of my friends, right? So we will do so these are a bit more challenging in nature. So one thing that I didn't actually cover through in detail is how to solve these kind of questions. Like, so we're looking at the one on the left. So the one on the left is a very critical kind of question that we need to solve lah. So I didn't necessarily go through what it means, right? So we'll be going through a very important concept today about what do we mean by how do we find the possible values for which w to the power n is real. So do take note, I may not be correct. I haven't looked at the solutions yet, but I just want to show you guys my thought process as I do this live. So because I think it will help that if I do it live so that you all can see what's in my mind. So the first one that let's do the left one first because the left one is more interesting. So you can see here that the number that they gave is a bit complicated. So let's do this B first. So let's just move this up first. Okay, never mind. We'll just do it like that then. Okay. Oh, I didn't know I can make it that big. Okay. See. Okay, so let's solve B first. Okay, so um B. Find the modulus and argument of the complex number. So we have W equals to 8 minus 2i 5 plus 3i. So we want the modulus and the argument of the complex number, hence find the possible value. So it's a very standard kind of question actually. So let's do the easy part first. So mod W, we learned it earlier already. It's actually just mod 8 minus 2i over mod 5 plus 3i. So how do we find the modulus of these numbers? So what I like to do is I personally like to represent this on an Argand diagram. So your Argand diagram is like your best friend here. So remember 8 and minus 2i. So what does 8 and minus 2i mean? It's just, you can think of it as like x and y coordinate. So your x coordinate is 8, and then your y coordinate is z, minus 2, my bad. So positive 8, so on the real axis, positive 8 and minus 2. So the number that we're looking at is here. So 8 minus 2. So, but the thing is that the distance here, right, is 2 and the distance here is 8. So how do we want to find the magnitude of this like kind of like vector like that? So you can see it's like vector. So how do we do it? So we actually just do Pythagoras theorem. So 8 square plus 2 square, and that is square root of 8 square is 64 plus 4, so 68. So this is equal to square root 68. So now we want 5 plus 3i. So same thing again. 5, 3. So here's 3, here is 5, and then this is square root 5 square plus 3 square. So 5 square plus 3 square is 25 plus 9, which is 25 plus 9 is uh 34, I think. Let me check my calculator. Where's my calculator? So yeah, sometimes when we do too much, we cannot remember what is our result. Anyways, I guess I gotten to rely on the calculator. So 34 and 8 square plus 2 square, 68. So 68 is 34. So which is equal to root 2. So now we have the modulus. Okay, so a rule of thumb that I learned, right, personally, right, is that for complex numbers, right, the numbers are all very, very nice one. Okay, let me qualify that. Most of the time, I always see that the number modulus, right, is always very nice numbers, like root 2, root 3, not like I don't know, like root 15 over 8. I've not seen that much kind of question. So it's usually a nice number. And usually for the angle, right, like this kind, right, that the argument, right, is a very nice number because they want you to represent in terms of pi. So usually it's a nice number, like, like pi over 3, pi over 6, like something that you recognize from the start. So that's just a rule of thumb lah. It might not be correct, but that's how I verify lah. So when I see something very strange, um I check again lah. But yeah lah, it's just something that I've seen lah. So So now that we know mod W equals to square root 2, now we want argument of W. So now we apply our kind of like logarithm principles plus 3i. So same thing again, how I do this is I will use my I will use my Argand diagram. So 5, 3. And then here is 8 minus 2 theta. So I want to find alpha and theta. So tangent alpha equals to 3 over 5. You see, this is the first time that we don't actually get a nice number. It's actually the first time I've encountered this actually. Most of the time it's always a nice number. Okay, I mean, yeah, at least now we know. So arctangent of alpha is alpha is arctangent of 3 over 5. So that's alpha. So now we want theta. So tangent theta, let's make it a bit smaller, equals to, sorry, it's a bit small, right? So tangent theta equals to 2 over 8, which is 1 over 4. So theta equals to tangent inverse 1 over 4. So argument of W equals to tangent inverse 1 over 4 minus tangent inverse 3 over 5. Let me just check whether there's any special value. I don't remember there being any special value, but it doesn't hurt to check. Okay, so let me just do a quick check, right? So 1 over 4 minus tangent inverse 3 over 5. So you don't get any nice number. So argument W is this. So just check that it's within minus pi and pi. So I just check it's like negative 16 degrees, which is okay, which is between minus pi and pi. So now that we have argument of W and modulus of W, now we do like the real deal, right, of this question, because this question is quite interesting. So now we want to find the possible values of W and such that we want to find the possible values of the positive integer n for which W to the power n is real. So the first thing I like to notice is that positive integer W power n is real. So these are the two things that we take. So there are many different variations. It can be negative integer, but usually it's positive integer. So we want W n to be a subset of the real numbers. Yeah, we want Wn to be an element of the real numbers. So how do we do this? When I look at, without any proper preparation, you look at it, you're just like, wow, I don't really know what to do. So I'm going to show you a trick here that some of you all may know, but is something that will need some practice. But after a while, right, once you practice, right, you'll get quite interesting. So let me pull out my notes here. It's actually in my notes, but I didn't go through it. So if so this is a type of question where we want to find, like, let's just say W power n is real, or W power n is positive, W power n is negative, W power n is purely imaginary, any kind of combination. So right, there's this, I'm going to show you 4 cases that usually questions like to ask. So the first case is that we want like something to be just purely real. Something can be real and positive. Something can be real and negative. And the last case, right, that I've seen, right, purely imaginary. So these are the 4 cases that we consider. So these are kind of 4 kinds of questions that always come up. So the magic comes here. We use our Argand diagram again. So when we look at real, let's look at the first case, case 1, real. Real means that the imaginary component is 0. What does it mean? It means that the number z has to be here, or here, because it can be positive or negative, because it's just real. Second case is when it's real and positive, then strictly speaking, it has to be here. So this is case 2. Case 1, case 1. So case 3, real and negative. Let's just denote this by W prime. So this is case 3. So case 4, purely imaginary, is more of a special one. We just want our complex number to be here or here, whereby the real component is 0. So how do we approach this? So right, what we do is we actually make use of arguments. We make use of arguments. Because if you think about it, the argument of a real number is actually the argument of a real number, right? Of let's just say a number x where x is real, right? Is actually it can be just be 0, pi, 2 pi, 3 pi. Because it can be 0, pi, 2 pi, 3 pi. So to generalize it, let it be k pi, where k is a real number. Okay, sorry, my bad. In this case, k is a integer for the first case. The second case, it's just called argument of y, whereby y the subset of the positive real numbers, right? Do in this case, right? Because some of you might ask about, like, I thought we restrict the argument to between pi and negative pi, right? So my answer to that is that, okay, firstly, I never actually think about it that way. So the second thing I'd like to explain is that in this case, right, we are not actually we are not like we're not actually like defining. It's like, this is like, how to say, it's like um they kind of mean, okay, let me see how to explain it in a simple way. Yeah, I mean, it's true. Yeah, we do restrict the argument to between negative pi and positive pi, but the thing is that in this case, right, um we're just looking for conditions whereby um the complex number is actually real, like its imaginary component is 0. We're not defining the complex number itself. We're just finding the possible cases whereby it's actually real. Because if you think about it, right? Okay, so let's just, okay, maybe because I never go through this concept yet. So what happens, right, if we have an argument of number z, right, and we find that it's actually outside of the region. Let's just say if it's actually 3 pi. And we know that 3 pi is outside of the range of pi and 2 minus pi. What we do is we factor it out by oh yeah, the ink is getting a bit fainter. See how do I make it better? Okay, yeah, I think it's better now. So what do we do, right? Is that if we have a 3 pi here, right? What we want to do is that we want to scale it up, scale by pi, 2 pi, or negative 2 pi, depending. So we scale by pi, 2 pi or negative 2 pi. So let's just say, right, if we have 3 pi, right, we want it to be pi, right? So we minus 2 pi so that it's equal to pi. 3 pi minus 2 pi is equal to pi. Or likewise, right, if we have negative 3 pi, right, we plus 2 pi. So we get negative pi. And then because it's outside the region, right, we plus another 2 pi again, such that it's actually pi. So yeah, we actually scale it by a factor of 2 pi, whether it's positive or negative. So likewise here, right, in this case, right, pi, 2 pi, 3 pi, right, it doesn't actually like matter so per se, because we can always scale this back to pi. because let's just say is the argument is actually 3 pi, right? Let's just say that for a certain value of n, w power of n, argument of w power n, right, is actually 3 pi, right? We can just change it to pi lor by minusing 2 pi. So it's actually it doesn't really matter. So we can always scale it back. We can always scale it back to the number itself. And furthermore, right, we're not finding the argument, we're not finding w power n. We're not actually finding the complex number w power n. We're just finding the instances, right, whereby, right, um that there's a complex number w, and if it's power to the n, right, and this resulting number, right, is actually um purely positive or purely imaginary in this case, we don't actually need to care about the number itself. But let's just say that maybe a question that actually asks you to use the value of n, right? And then if you want to define it, right, you find that this value of n, right, actually gives you 3 pi, right? What you do is you just scale it back, lor. So yeah, that's about it. It's nothing really too complicated. It's just that maybe I didn't go through this concept that we need to scale it up or down by a factor of 2 pi. So I hope that helps. I personally didn't think about it that way. It's a good question actually. So now we consider second case, whereby it's real and positive. So real and positive means that we are looking at here. So real and positive means that sorry, real and positive is here. So real and positive, case case two, real and positive is we run it such that the argument of w power of n, right, is 2 pi, 4 pi, 6 pi. So it's like 2 pi, 4 pi, 6 pi. Yeah, you get the gist of it. So equals to 2k pi, where k is a subset of the element of integer. So z is integer. So yeah. So if we want real and negative, we want argument w power n equals to pi, 3 pi, 5 pi. So this one we do 2k plus 1 pi, where yeah, 2k plus 1 pi. Same thing again, where k is the element of the integers. Just that we can include 0 in this case, so k can be 0 in this case. Just take note, k can be negative, by the way. Nobody's saying that k cannot be negative, so just take note, k can be negative also, but k has to be an integer. Yes, so example, if k equals 0, right, this is just pi lah. If k equals to 1, it's just 3 pi and then 5 pi. So another way that I do it, right, what I do is so because I cannot remember, right, I sometimes do like that also. If I want real and if I want real and like how do I say pure real and negative, right? Sometimes I like to do actually wait a moment, that's wrong. So what I will do, a misconception I made was that I did k over 2 pi. But the thing is that k over 2 pi is wrong lah. Is this actually the case for purely imaginary? Yep, so the last one, right, case 4, right? So case 4, right? So case 4 is purely imaginary. So let's just say argument w power of n equals to pi over 2, 3 pi over 2, 5 pi over 2, which is actually k over 2 pi. Okay, you can see it can be 2k plus 1 pi over 2 or k pi over 2, depending on what k is. But in this case, k has to be odd lah. But this is like k is integer lah. So actually in the end still use this lah. Okay, I think I might confuse you guys. So in summary, my bad. We want to use this case 2k plus 1. Also, is there a possibility that they might ask purely imaginary and positive? Who knows? It's possible, but I'm sure you guys will know how to do it anyway. So I'll leave it as an exercise to the reader or the listener in this case to derive it. Um, but you can let me know if you see such a question because I really never seen such a question before. So yeah. Okay, back to the actual question. So now we look at this question. So we want W power n to be real. So W power of n is real. So real, what does it mean? We means argument of W power of n is actually equal to, so let me think real is, so we want it to be like pi and 3 pi, so pi 3 pi, so 2k pi lah, right? Or k pi, yeah, k pi, sorry, k pi, yeah, because k like can be pi, 2 pi, 3 pi, yeah, my bad. So remember we apply our rules, right? So the n can bring down, we call n argument of w equals to k pi. So you remember why I said that usually they give you nice numbers? It's because when you have such a very strange function like this, right? It's not very like nice. But since the question, this is the first time I actually seen this. Since the question is a bit strange, so let's use this. So tangent inverse 1 over 4 minus tangent inverse 3 over 5 equals to k pi. So we want the value of n such that you get uh, a positive, you get an integer value of k. So how can we do this? Let me just look at the question again. So we want n to be a positive integer for which w power n is real. So you must take note firstly is that this must be positive, and then this must be an integer also. Did they say integer? Okay, integer also. So positive integer. So the catch comes here. Um, okay, so let me see how do I simplify this function. Uh, okay, so that's why I always say usually I always give you a nice number for the argument. So I'm a bit confused here, like what is. So that's why I say that they always give you a nice number so that the pi and pi can cancel out. If not, it's really a bit a convoluted function. So um hmm. So since this question didn't like say that you can use the calculator, maybe why don't we try to simplify this function? Maybe you'll get something nice. But yeah, a rule of thumb is that, let me put up my GC. A rule of thumb is that it'll always be a nice number lah. Then this is the exact reason why lah. Maybe I didn't simplify the rationalize the thing. Oh wait, this is just 1 minus I. Okay, then that makes sense. It'll just be yeah, okay, it'll just be pi over 4. Okay, so 11 my. So now that we know that this W, right, is actually just 1 minus I. So 1 minus I. So 1 minus I is just 1 minus 1. So theta, so we get that theta equals to pi over 4. So because tangent theta equals to 1. So let's use the new argument, and argument W equals to k pi. K pi. So n pi over 4 equals to k pi. So n equals to 4k. Or maybe k equals to n over 4. So in this case, right, since n is positive, then n equals to 4, n equals to 8. When n equals to 4, k equals to 1, k equals to 2. So how many values do they want? Or they want the smallest value or possible values. Okay, so since they want possible values, right? So n equals to 4, n equals to 8, n equals to 12. So then, right, what you can do is you can say that n equals to 4. Let it be a constant. So let it be for b, where b is a subset of positive integers, because you cannot have a negative integer, so that's how we'll do it. So n equals to 4b, and b is element of integers, so done. So that's how we do the first question. It's a bit long, but I just want to emphasize this really important point. So the takeaway is really to consider the 4 cases here, and then the corresponding arguments that they have. Right, okay. So now that we have conquered the first question, let's erase everything and let's do the second question now. So let me erase everything first. This whiteboard is quite interesting because like it's really big. So wait, erase entire strokes. So let me erase everything first. I hope you all can see the screen. Okay, yeah, so yeah, it's my first few times making it, so yeah. Okay, now let's do the second one. So now let's do the second one. Okay, this looks a bit complicated. Okay, so let's try now. So 17a. Okay, I think the stroke is here. Okay, so show that 1 minus I tan theta 1 plus I tan theta equals to e to the minus I 2 theta. So, hmm, let me think. How do I want to do this question? So either I attempt to make the left hand side go to the right hand side, or the right hand side go to the left hand side. My gut feel tells me that I want to make the left hand side equals the right hand side, not right hand side. So let's try to make the left hand side first. So theta 1 plus I tan theta. So maybe we can rationalize the function. Let's multiply both sides of 1 plus I tan theta 1 plus I tan theta. Okay, I have 10 minutes left, so I might overrun this a little bit. So yeah, we multiply, so we get 1 plus tangent square theta over 1 plus 2i tangent theta minus tangent square theta. So 1 plus tangent square theta. Okay, so e to the I2 theta, right, is actually equals to, so actually, right, we can change this to e to the minus 2i theta. So remember we talked about the exponential form, right? This is r cosine theta plus I sine theta. So do we get that r is 1? So it's actually just cosine minus 2 theta, because theta is actually, the argument here is actually minus 2 theta plus I sine minus 2 theta. So what we get is, because cosine minus 2 theta is actually just equal to cosine 2 theta, so and then equals to minus I sine 2 theta. So now that we have this, so we're looking for this. So we're trying to see how can we make the right hand side go to the left hand side. So now that we have some idea, so let's continue. Let me make sure I copied it correctly. 1 minus I tan theta. So okay, let me see. So okay, so I assume you all know how to expand lah. A square plus b square. So 1 plus tangent square theta. And then we have a square plus 2ab plus b square. So we have I square tangent square theta. So I square got negative 1. So that's how it accounts for the thing. So no, I'm multiplying by, oh yeah, 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 my bad. We should be multiplying by the conjugate. Yeah, yeah, yeah. I multiply it by wrongly. Okay, so okay, my bad. Let's do it again. So 1 minus I tan theta, 1 plus I tan theta, we times 1 minus I tan theta, 1 minus I tan theta. So we get 1 minus 2I tan theta minus tangent square theta equals to 1 minus tangent 1 plus tangent square theta. So 1 plus tangent square theta is secant square theta. So 1 minus tangent square theta 2I tangent theta. Okay, let me see what can we do. Well, this is a bit challenging. So sometimes, right, when you get all these like really like weird like questions, right, you can just skip it and use the result first, and then you do the other parts first. After that, you get the you use those previous it's like you do the next parts first. After that, you go back to the first part if you cannot prove it. So let me just check. A square plus b square. So you have 1 plus tangent square theta. So and that is secant square theta. So we have something, right? So 1 minus tangent square theta, secant square theta. Okay, let me see what can we do here. Okay, I think I saw it. Okay, so because right, 1 plus tangent square is secant square theta, right? Then 1 over secant square theta is actually cosine square theta. 1 minus tangent square theta minus 2I tan theta. So cosine square theta. Let me express all this in terms of sine square theta over cosine square theta minus 2I sine theta over cosine theta. So we expand everything in. You have cosine square theta minus sine square theta minus 2I sine theta cosine theta. So I think you'll see already, right? So cosine square theta minus sine square theta, if MF26, right, is a cosine 2 theta. Sine theta, 2 sine theta cosine theta is actually I sine 2 theta. Sine theta plus I sine 2 theta. Okay, so now we go backwards. So this is R, which is 1 cosine minus 2 theta plus I sine minus 2 theta. And therefore, we get e to the minus 2I theta, which equals to RHS. Okay, sure. Okay, that's a bit tedious, but I think you all get the gist of it. So this is just pure manipulation. Okay, so now that we have proven part A, so usually, right, part A helps you in part B. So I only have 3 minutes left, so I'm going to stop the video for now, and I'm going to come back to it. Sorry, I'm going to stop the video recording first, and I'm going to continue in the next video. So just hang on a moment. Yeah, so this will continue. I'll complete the questions. So yeah, see you in the next video.